Before it was totally sharp, but my presentation somehow seems to. Okay, let us go to the slide. Okay. Just making sure that this works. People can see the presentation already. Oh, this works.
It's working.
Yeah.
I will briefly introduce you.
Yeah.
Then we will take questions after the initial presentation.
Yeah.
Then it's the questions we will take in turn, and you have around 45 minutes. If you need extra minutes, it's fine.
Yeah.
So it's entirely up to you.
Okay. So it will take me roughly 45. Can you perhaps show to me that it's 40 minutes?
Yes.
Or perhaps I should do that with the phone?
Here, so I can see your slides.
Okay.
And just when it's 40 minutes, I will write 40 and then show it.
Super.
Okay.
Super. Great.
In the meantime, we can wait while people come into the room.
Perfect. We have time, I think, still. Yeah, of course. Thank you. Kilki is the same name
My
as
father.
Asir. Ah, okay. Such a pleasure. Nice to meet you.
So great pleasure to see you here.
Thank you.
And it's here. Together. Thank you very much.
It's a pleasure to be here. See, is it Kilkish or Kilkish? Kilkish? Kilkish. I saw it because Turkish. It must be Kilkish.
Yes.
Yeah. Okay. So we know each other so well that I don't know how to pronounce the second name.
Yes, Kilkish.
Kilkish. Okay.
I will stand there just to make sure people are sitting and taking their seats.
Sure.
And put the pressure because it's 11:30.
Okay.
Good day, SDEWES! It's a great pleasure to introduce our plenary invited speaker, Professor Keiwan Rihahi, who is Director of the Energy, Climate and Environment Program at the International Institute for Applied Systems Analysis, IASA. Keiwan Rihahi has ample experience in interdisciplinary research of climate change response options, actively working with the Intergovernmental Panel on Climate Change, IPCC, where I had the great honor of working with Keiwan. During the 6th assessment cycle, Keiwan served as a coordinating lead author of one of the main pillars and most important aspects of the Working Group 3 report, Mitigation Pathways Compatible with Long-Term Goals. Previously, his service as lead author and review editor in international assessments spans the Global Energy Assessment, the World in 2050, and IPCC's 3rd, 4th, and 5th assessment reports, as well as special reports. He lectures as a visiting professor of energy systems analysis at the Graz University of Technology and is a fellow of the Payne Institute for Public Policy. He also serves as an external faculty member at the Institute for Advanced Study at the University of Amsterdam. As the most influential climate scientist worldwide, he ranks first in Reuters' list of the world's top climate scientists, and he is one of 23 researchers globally taking place in the list of highly cited researchers of Clarivate in 3 multidisciplinary categories: geosciences, social sciences, and environment and ecology. To provide focused advice for accelerating progress on sustainable development goals, UN Secretary General Antonio Guterres appointed him to a 10-member group of high-level representatives of civil society, the private sector, and scientific community. In March 2022, he was also appointed to the European Scientific Advisory Board on Climate Change to provide scientific advice to underpin climate action and efforts by the EU to reach climate neutrality by 2050. Keiwan, the floor is all yours for your invited lecture here in Dubrovnik, Rapid System Transformations for Addressing Global Sustainability Challenges.
Yeah, thank you, Sia, for this very kind introduction. It's a real pleasure to be here today. I'm honored that I can speak, that I can give this plenary lecture. I want to also thank particularly Neven Dujic and the organizers to inviting me. It's really great to be here. So I will talk about rapid systems transformations. This will include some of the insights of the work that I could contribute to the 6th assessment report, but it will also include some of my own research biases and insights that we gained since the 6th assessment report was actually finalized last year. But let me start perhaps with some thoughts about the current energy system. So lots of my talk will actually focus on energy and the importance of energy for sustainable development, but also the importance for energy underpinning any of our activities and being also the main source of the levels of well-being and the levels of affluence that we have achieved. So without the provision of fossil fuels, whose main advantage is a very high energy density, which underpins our economic activities, it would have been very difficult to achieve similar productivity levels as we have them today. At the same time, the current system has a number of main challenges. So we basically created, at the one hand, advantages, but we have to pay also with trade-offs on many different areas. Perhaps one of the biggest trade-offs is that there are still billions of people who don't have access to clean energy, who don't have access to electricity, don't have access to clean cooking. That's the biggest source of mortality on the planet, energy-related mortality. So there are millions of people, particularly women and children, dying because of indoor air pollution by cooking from using biomass, dead wood within houses, and not having access to electric cookers or LPG cookers, for example. The other, perhaps more discussed challenges, of course, here are that we have increasingly trade-offs with biodiversity and food production from the energy sector because of the land needs. Energy is a main source for air pollution. We need water for energy, and we have created energy scarcity in some areas, even though that energy is not the main source of water use. And of course, energy is the main source for greenhouse gas emissions and is the main cause of climate change. And we need to decarbonize, and therefore the energy sector. So we need to solve all of these problems together, and in addition, energy has another important dimension, which is the energy security dimension, because energy is not distributed evenly across the planet, and we need to basically import a lot of the energy. So I want to focus a little bit, perhaps particularly on this latter problem, because we need deep structural changes in order to solve the climate problem. And very often I hear the question, okay, why 1.5 degrees? Wouldn't be 2 degrees be enough? It makes a big difference. Many studies actually show us that every tenth of a degree matters. I've selected here a study that we looked into, where we at IASA have looked into the difference in terms of population at risks on multi-sectoral extreme events. These are basically the exposure to extreme events when droughts and floods and many, many extreme events would come together at very high risk. And you can see here, more or less, if I can show this to you, this is the population in the future. This is the fraction of people who would be exposed to multi-sectoral events. And the black line, the black part of that is actually the fraction of the population who is very vulnerable and has also limited adaptation capacity at the same time, because these are the people that we are really worried about. And you can see the big difference between 1.5 degrees and 2 degrees. So basically you have almost a doubling of the vulnerable people. And at 2 degrees, we have still a vulnerability of 500 million people being exposed. This is an average value. There's quite some uncertainty around it. This is assuming an intermediate socioeconomic development into the future. For those who know SSPs, this is an SSP2 projection. And here you can see how this exposure and vulnerability changes at 3 degrees. And that is the motivation to basically also written in the Paris Agreement to basically pursue, to limit climate change well below 2 degrees, but to pursue also 1.5 degrees, because there is a big difference between 2 and 1.5 degrees. And then when we start with 1.5 degrees, of course, the big question is how much time is left? When do we need to achieve net zero emissions, or how many emissions can we still vent into the atmosphere? And most of you will know these numbers, of course, but just as a reminder, in the sixth assessment report, we assessed the remaining budget that we can still vent into the atmosphere to be around 500 gigatons when we are happy with a 50-50 chance. Climate is uncertain, so for a 50% chance to keep warming below 1.5 degrees, we have 500 gigatons left. With a likely chance, how the IPCC calls it, a 66% chance, we have only 400 gigatons left. And these were the numbers assessed more than 2 years ago, 3 years ago. Uncertainties around these 400 gigatons are around 220 gigatons, because you have also non-CO2 emissions, and you have roughly 420 gigatons because of the geophysical uncertainties. This sounds big, but is actually not so big. Sorry for this additional red dot here. It seems I have recorded it at some point. Forgot to delete the recording. Is this big? No, it's not. It's not very big. Current emissions are at the moment already at 45 gigatons of CO2. If you make a quick calculation, you can see that this would mean at current emissions less than 10 years, we will surpass the 1.5 degree level. Actually, we have done 3 years relatively little. The budget is now more around 200 gigatons of CO2. Which means that it's just a question of a few years that we will hear the first time from TV that we have overshooted the 1.5 degree target. Is the 1.5 degree target dead because of that? No, it is not, because all the IPCC scenarios actually assume that we will in the future have a slight overshoot in terms of temperatures to 1.6, 1.7 degrees, and then need to think about how we can manage to reduce temperatures again, and I will come back to that, how we can perhaps achieve this. So overshooting the 1.5 degree target doesn't make the 1.5 degree target dead. It just means that we need to get as quickly as possible to net zero emissions and then think about how to turn temperatures back again. Yeah, I mentioned this already. We are not on track for the 1.5 degree target. Obviously, emissions are still increasing, and at the same time, I want also to mention the positive aspects that we have achieved since the Paris Agreement. So the Paris Agreement might not have stopped emissions or even turned basically bended the curve down again. But because of the Paris Agreement, I would argue we have many, many zero emissions targets and many new policies into the system which are ramping up. So we have in the meantime almost 1,000 cities who have a net zero target. Many developing countries have in the meantime a net zero target. And because of mainstreaming of climate policy, we also observe a major push in innovation. As you know, solar, wind, electric batteries have diffused quickly into the market, and because of that diffusion into the market, the costs of the production of these technologies have come down. And in many parts of the world, in the meantime, particularly there where you need to build new infrastructure, renewable energy is competitive and is often cheaper than fossil fuel alternatives. So that's the good news. If you think about the political part of it, actually here one has to be very careful what to conclude. So how much legislation is actually there already in different countries, and will that be enough in order, or how much temperature change will that legislation result in? And that's something that you can see here. A figure by my colleague Jori Rögele. I forgot to add the reference to the paper. It just came out in Nature a few weeks ago. And what you can see here, up here, is basically the uncertainty of the future emissions pathways. If you think about all the legislated policies that we have today and how they might develop into the future. So quite some uncertainty. And this is the distribution of temperature outcomes if you take those emissions pathway and put them into the models. Basically, the median of this line is something around 2.5 to 3 degrees. This is where we are heading towards at the moment if you just take what is legislated in different countries. If you compare this to this one, this is actually, if you take all the legislated policies and you add also all zero emission pledges of different countries. So India said it would be at net zero in 2070, China said 2060, EU 2050, Austria 2040. If you add all of them, you get actually to some temperature change distribution which looks like this, and emissions pathways which looks like this, and it is a slight. It is basically the median is around 1.5 to 2 degrees, 1.7 degrees as a peak temperature from that pathway. So one could argue, yeah, we just need to do what countries have pledged so far. But actually, the question is, are these pledges credible or not? And if you look into the underlying credibility of the pledges, you get to a different picture. You get to a picture which looks like this. Basically, those pledges which have been made, which have also some substantiation in a process within the countries to actually also enforce the net zero targets, you get to this red line here. So you get a slight decline. The further you go down here, the lower becomes the confidence in the pledges that the countries make. So the gap between what is, so there is perhaps the ambition gap of different countries has been reduced significantly, but the implementation gap is still very big. So we need to go from ambition to implementation, and this is particularly the case in many countries of the developing world. In order to achieve that, we need to accelerate, obviously, the system transformation, and I want to come to some of the main building blocks, which is very rapid and immediate greenhouse gas emissions reduction, achieving net zero around 2050, for which we have a range of technologies available, and where behavioral change and lifestyles into the future can play a key role, which is also connected to our value system. With behavioral change, I don't mean actually sacrifice, but I mean thinking about new ways of service provisioning and also service consumption. And then we need, of course, in order to achieve this, increase investments in clean and low carbon options. And the two, I think, good news here is, on the one hand, that if you look into purely the technical and economic options that are there, those are actually sufficient to reduce current emissions by about 50% in 2030 at a pure technological and economic basis, and they can be achieved at prices of less than $100 per ton of CO2. We have, of course, in many countries, neither $100 per ton of CO2 nor the legislation, but techno-economically, you can see here that the potentials are relatively large. This is a picture from the IPCC SPM. Here you can see the gigatons of emissions reduction possibilities, and particularly interesting are the blue ones, because the blue ones are emissions reductions that can be achieved cost effectively. So you would actually even get an economic benefit by switching there. And the economic benefits are particularly at the supply side, for solar and wind, and in the transportation sector and in the building sector, if you look at this very carefully. Potentials are also very large. If you go to higher costs, 4 gigatons, this is roughly 10% of the current CO2 emissions. So if you cannot add them strictly up, because if you reduce emissions in one side of the energy sector, the potential to reduce emissions in the other side is, of course, reduced. But if you add them up in a sensible way, you can achieve 50% emissions reduction by 2030 from these graphs. The second, perhaps good news, not good news to you, because as an expert you will I think, know the basic principle, is that if you talk about carbon neutrality, this doesn't mean that we have to reduce emissions in every sector to zero. It's going to be, the question will be there's no question. You will have basically it is necessary to achieve a balance between emissions, residual emissions that are left in sectors which are traditionally perhaps more difficult to abate, and a planetary sink that we need to achieve, so negative emissions in other sectors where it's possible basically to remove CO2 from the atmosphere. And this is a typical transformation pathway. This shows you that some sectors stay positive while other sectors become negative, calculated with different integrated assessment models. And if you think about how much does this sink need to be, this sink, of course, depends on the emissions reduction potentials in the sectors. And if you look at different studies in the literature, we can see that this negative emissions sink, first of all, there is an uncertainty across different models that assess this sink. So these are different models here. These are the positive emissions, these are negative emissions at the time of net zero, which is in these models now between 2050 and 2070. The smallest estimates are around 5 gigatons, the largest estimates are around 10 gigatons, which means that the majority of the job is going to be mitigation. But there is this residual negative emissions tail that we need to achieve. And many of the studies show that there is a combination of possible negative emissions in the energy supply sector and so-called nature-based solutions, which is afforestation, increasing of, improving basically the soil carbon content. This means, though, also that if you think from a systemic perspective, what needs to happen is that when we are at the point of net zero of the full system, some of the sectors have to be actually at net zero earlier than that. So the forest sector and the energy supply sector, particularly the electricity sector, needs to achieve net zero earlier if we expect that those sectors contribute with negative emissions in order to achieve net zero. And this is what you can see here is basically the distribution of the different sectors. This is the time of net zero globally, and minus means that, for example, the energy supply sector in a large fraction of the IPCC scenarios has been 10 years earlier at net zero. And the afforestation sector actually on average has been 30 years or even 40 years earlier at net zero, because it's easier to achieve, of course, net zero in the forest sector, because stopping afforestation would help to increase the planetary sink in terms of forests. And on the other side, of course, most of the studies show that industrial processes and energy demand sectors, particularly industry and transportation, might not be net zero for some years to come after the global system has achieved net zero. Okay, so let me perhaps continue with two possible perspectives of how to achieve this transformation. So if you look at the literature, there are basically, there is a conventional perspective of how this transformation will happen, and a big focus on technological change and innovations on the supply side. Infrastructure is important, but a supply side driven system where basically inertia in policy, social and technological change leads to an overshoot of the 1.5-degree target, which need then in the long term be compensated with a lot of negative emissions in order to bring temperatures back to 1.5 degrees. The other perspective here is, of course, thinking about how can we accelerate the transformation, and there is an increasing body of literature that shows that to demand-side solutions and to granular technologies, we can accelerate the transformation, particularly if we focus on end-use changes and demand-side innovation and behavioral change. Basically, the idea is to focus on small-scale, granular, distributed technologies which are digitally connected and steer basically the transformation towards accelerated transformation of also the supply side options. And the advantage of limiting this overshoot is, of course, the lower the overshoot is, the less negative emissions you might need. And some of the studies show that actually you might not need technological negative emissions options. It might be sufficient to do the afforestation and the soil carbon enhancements if we are quick enough with getting to net zero and if we can accelerate it. Why this demand side focus? Yeah, this demand side focus is particularly important because at the demand side, this is where most of the efficiency potentials are. So if you look at how we basically have losses at the different energy conversion steps in the energy system, most of the losses happen actually at the final energy level. And at the end-use level, this is something that you can see here quite nicely, from 511 exajoules, which go into the total energy consumption of the world. We use as a service only 72. And after the secondary conversion, we basically, at the level where the consumer uses, basically at the level of the provisioning system, we lose most of that energy. So focusing on that part is also an efficiency is also an efficiency question, and you can see this basically across all different sectors. The industrial sector, transport sector, even material and irrigation sector has the same type of dependency as well as the building sector. So we can basically tap into the full potential of the efficiency we can tap into larger potential of efficiency by focusing on the provisioning system and looking at the problem from the demand side. The other big advantage is, of course, that small-scale technologies generally learn faster. So if you think about the difference between a solar PV cell and a nuclear power plant, the difference is that if you build a nuclear power plant, you have built 1 gigawatt capacity and you build it exactly once. You don't learn much because you have built it once. In order to build 1 gigawatt of solar PV capacity, you have to build many cells. So you repeat the same process of innovation and construction many times, and that's why a solar PV cell after 1 gigawatt has learned much more than a big nuclear power plant. And that we can see in the empirical studies across all technologies, also in the transport sector, also in the chemical sector, etc. So we have faster learning, we have faster diffusion because granular technologies can diffuse also into smaller markets much more quicker. We create also better access by distributed granular technology, and we have also lower investment risk. So you can distribute the investment risk among many investors. You cannot build a nuclear power plant not even as a company. You need a state behind your activity in order to manage the investment, in order to de-risk the investment, because that investment needs to be there also for many years. So that's why granular technology focus accelerates the diffusion and also has many other advantages here. How would this look like at the end? I mean, it's about creating and relying on many disruptive end-user innovations. And what they have all in common is that we would move away from the system where basically the focus of it is that the consumer owns the service to a system where we center stage usership. So moving from ownership to usership. What do I mean here? Basically, the focus should not be, the classical example here would be, the focus is not to own a car. The focus is that you go most conveniently, most quickly, and most economically from A to B. The mobility is the focus. And then, very often, the car will not be the best option. But of course, from the value, from your point of the private value system, if we value owning the car more than the service that it provides, then of course your incentive will be completely different. So we need to move from ownership to usership, and that will enable that we have a sharing economy with better service provisioning system than the current one. And the key to that is that we move also from disconnected, automized individual technologies to integrated, connected systems where the technologies digitally communicate with each other, because then you can also, to sharing, increase the service quality. Yeah, so that is extremely important. There are many different studies who show the big benefit from integrated digital mobility services. Particularly the OECD ITF has done studies about many cities in Europe, but also outside Europe. I picked here one example, Dublin, where you can see that the shared mobility scenarios in Dublin, where a pure service focus basically means that you, with a small fraction of the vehicle fleet of about 2% and increased and improved public mobility, you can actually provide a better service than with the 98% of the cars that you don't use. So you just need 2% of the cars to provide the same mobility service, and you create many co-benefits of that. So people need to drive less. We have less emissions. We have particularly less congestion. So the biggest benefit is sometimes not even the climate benefit. It's the biggest benefit might be congestions and by freeing up space. So we got used to live in a city where the street is dominated by the use of the car. So we have 3 lanes, 2 lanes are parking lanes, because everybody needs to always own car, and 1 lane is for driving, and we have 1 square meter to walk perhaps to our car, because it's not expected that we use the street for anything else than driving. In a city where you have only 2% of the cars, no car is standing in the city. It's not necessary, right? So but you still have access to a car, but it's not standing there. It is perhaps coming to you, and this is, I think, the big change that we need to envisage, and it is already happening in some cities in Europe, and I think Dutch cities, smaller Dutch cities, are a nice example of in which direction we need to go. The other important aspect of moving from this is the so-called information and communication technology convergence, which is to move away from the thinking that we need to improve the efficiency of the appliances to a more system thinking where the service of the efficiency is the main thing that we focus on. And a good example for that is, for example, the mobile phone. The mobile phone integrates, it's not only used for calling, like the old service, the telephone, but it includes many, many different other services. And by including all these other services, what it allows us is that we don't need many of these other appliances. And we don't need the energy consumption and the material consumption of those other appliances. So the indirect effect of a mobile phone, because of the digital integration, is bigger than actually its main service. So if you make a calculation and you look at the energy that you need to build the mobile phone compared to the energy that you need to build all these other devices that it replaces, you can see already there that effect is very big. If you think about the energy use of the mobile phone and compare it to the energy use of all these other devices, you have another a big factor here. So using digitalization in a way that we provide provisioning service efficiency is extremely important. Let me jump over this because of time reasons. But basically, I was talking about many possible benefits of digitalization. Just to wrap this up, so we can accelerate system change, we can improve efficiency, we can enhance the quality of the service, we can also improve access, and we also improve affordability. Just imagine a mobility system where you don't have to buy the car yourself, but you basically share also cost with others. Environmental performance is improved, and you can also use digitalization, of course, to integrate renewables by switching to a system where basically the utility provider has control over all high-capacity appliances that basically can go up and down. But I don't have to tell this to you. I think you are the main experts in the field. The big question is, can we steer digitalization to create all of those benefits? Because there is also a big risk that digitalization actually is going into a different direction. So with digitalization, we can increase equity, but we can also, and this is what we see right now, we can increase equity because of better access and more economic access to all sorts of services. But we can also create a world where equity is actually worsened because the capital is accumulated in the hands of a few actors who actually are controlling those sharing systems. Yeah? So we have to be very careful how we implement digitalization, and we need to have measures in place which make sure that we create a new equitable system. The same is with the political agency. Digitalization can help to bring information to all of us so that we have access to reliable information and can can basically participate also in the political system. But digitalization can also be used to create bubbles, and we see both happening at the same time. Yeah? So we as scientists, the access to information has never been better than nowadays. At the same time, we see also this movement that information is actually controlled in a way that people only get the information which they think is convenient for them. And it's also a dangerous development. Yeah? So we can create political agency, but we can also destroy it with digitalization. And this is very important. And the same is also for the planetary stability. We need political agency for the planetary stability. We need to improve equity. We can use digitalization for both. And we can, of course, also to digitalization have these all other benefits that I mentioned. We can make the system more efficient, but at the same time, we can also create a lot of new services and increase our energy demand. And this is then the negative side of it. And we need to find ways and particularly new policy systems or policies that would steer digitalization into the right direction. Let me jump also over this and get to a different other topic. I didn't want to leave you with the impression that we just need to look at demand. I think there are lots of innovation in energy supply that we need to better understand. My own work and our work at IASA is now not only focusing on the system integration and on future scenarios, but one thing that we are particularly interested to understand is how can we store better energy in the future. If we want to integrate renewables, we need to store energy. In the minds of most of us is, of course, there is the battery, there is the pumped hydro, which is, these are technologies that are in everybody's mind. I would argue there are many out-of-the-box and unconventional technologies which we do not explore sufficiently. And there are potentials around us that we can tap into. And these are a few more unconventional ones are, for example, lift energy that can be used. Basically, when you have too much energy, too much electricity, let's say at midday, the lift brings some weight up into the higher floors, and when you have too little energy in the city, you can let the lift produce electricity thereafter. This was a paper that we wrote 5 years ago. There are now 3 patents out there, and in New York there are 3 skyscrapers who are implementing this now, right? Just as an energy efficiency measure for themselves right now, and perhaps so this is these are the smaller granular technologies that can basically get into the market. Something that I'm convinced of that we will move towards is we have in alpine regions pumped hydro, right? So we can pump water up and then let it to a turbine. It's a very elegant way to store energy. If you have a coastal area, you can have Beyoncé energy storage plants. Basically, you put things underwater when you have excess energy. They want to come back up, and then you can use that pushback from the water to produce energy again. Yeah, so it's basically the same concept as the hydro power plant, just underwater and in the other direction. Long-term solutions probably are the creation of a compressed air or hydrogen link in the deep ocean. Hydrogen has a very low energy density, as you all know. It has also, it needs, if you don't pressurize it, you need to cool it quite a lot to store it. But if you pump actually hydrogen into vessels that are filled with sand, you can create a link and a deep ocean hydrogen link and share hydrogen across far distances without the need of a lot of energy. So this is all out of the box. This is not built now, but I think we need to think about all these different alternatives. What we have started to do at IASA is we started to look into the regional storage potentials that are there, as well as the costs, and they are, for different options, the potentials are very different, but that's the interesting thing. So there will be a granular and different storage options that one can use. In our modeling, we have now included, particularly in addition to lift storage, in addition to seasonal pumped hydro, of course, also lift storage, electric truck gravity energy storage, and mountain gravity. And we want to add the Beyoncé energy storage as well to look at how this can help with the integration. Looking into different storage options is of course also very important because different storage options are sometimes useful to help with daily variation or weekly variation of energy, which is necessary. But the big and difficult part is the seasonal storage needs, and also the interannual or pluriannual storage. And not all of these options are actually really useful and available for these long-term storage possibilities. This is, I think, a useful way to think about it, what in terms of the time that you need to store things, and in terms of the size and capacity where storage capacity can become available. And you can see here, that's the domain of batteries, daily and weekly, and the lift energy storage option, for example, that I showed you. Everything that has to do with deep ocean, pumped storage, and particularly synthetic fuels, hydrogen, ammoniac, etc., is of course, these are the long-term options, and we need a blend, we need both of them at the end in the system. I don't know exactly how am I in time? How many? 7 minutes? Okay, so I need to accelerate. So let me move perhaps to another critical question, which we are asked very often, is are these changes that we are these changes and the pace at which the changes are happening, for example, in the global IPCC scenarios, is this feasible, and is it possible to design a transformation which is also perceived just by everybody? So that's I think a really important question, which the community starts to explore in a more systematic way. This has to do, at the one hand, with the fact that mitigation costs are very different across different regions. I'm not sure whether you knew that if you look into the mitigation in a cost-effective strategy to mitigate or to reduce emissions globally, that the economic costs of that mitigation are actually the lowest in Europe and in the US. So these are the ranges of mitigation costs in different regions from the IPCC report, from the chapter that I actually coordinated. Here we see the mitigation costs in Europe. They are roughly around 1%, a little bit between 1 and 2.5%. This is the global average mitigation costs. And this is the mitigation cost in the Middle East, in Russia, reforming economies, Africa, India, which are generally above the global average. And this perception of who has to bear the costs and for whom it will be economically more expensive or less expensive, of course, creates also tensions in terms of who has to do what. Why are the mitigation costs low in Europe? The mitigation costs in Europe are low because of a double dividend. At the one hand, we basically we have to pay initially, make an upfront investment to increase renewables and to change our system. But because of that, we rely much more on local sources, and the value chain of the energy sector remains within Europe. So what we don't have to do then, we don't have to pay for imports, which is always bad for economic development. So and countries which generally have a lot of benefits from the fossil fuel trade, those who produce the fossil fuels today, for them it's of course getting very expensive because they lose a whole part of their economy. And that's why costs in the Middle East, and in Russia will be around 10%, and costs in Europe will be only around 2%. So that's something that we need to keep in mind, and we need to also think about how do we get those countries on board when we make this transformation. But feasibility is not only about costs. One has to look into feasibility in a systematic way, and something that what we have done also in the IPCC report. This is work by my colleague Elina Bruchin that she led and was part of, is that we can look into the transformations and the results that we see from different scenarios in terms of different feasibility dimensions. So there is one dimension is geophysical feasibility. Do we have the potentials really out there? Another dimension is the economics. I just mentioned a little bit about the economics, but it's broader than who has to pay. Then there is the technological feasibility. To which extent do these scenarios in the long term depend on technologies, for example, which are not yet in the market? We don't take CO2 out of the atmosphere, and these scenarios in the long term do this. So some of them have a higher technological risk than others. What is the socio-cultural change that these scenarios assume? So the many benefits that I described earlier in terms of trying to limit energy demand are only realizable with a certain value change. And there is, of course, the risk that that value change is not going to be accepted in our society. So that's also a feasibility challenge. So geophysical, economic, technological, sociocultural, and then finally, perhaps the most important factor, actually we found out that this is the most important factor, is the institutional and the governance dimension. So do we have in all parts of the world the governance and the institutions that would actually be able to manage these structural changes? And if we look into the IPCC scenarios and apply a set of very detailed assumptions about how to quantify those feasibility challenges, the biggest feasibility challenge has been the institutional one. So more than half of the scenarios basically assume emissions reductions in the developing world where it is probably questionable whether we can achieve them under current institutional capacity. So this means also that this doesn't mean that this is totally infeasible. It's about, this is not black and white, but this is about the risk that we need to understand, because we then also understand that it's not sufficient that we in Europe manage the transition. We need to help other countries that they have stable governance capacity to make the transition at home as well. So that's also part of our responsibility, I think. And then let me conclude perhaps with a few slides. So that's basically another, let me move from feasibility to just transitions. So what you can see here is basically a figure that shows the investment needs, ranges of, these are ranges of investment needs across, for example, different regions. These are the investments into zero carbon or into, let's say, sustainable and climate-friendly technologies today. And this is the increase in investments that we need everywhere. This actually is a figure which was proposed to be part of the summary for policymakers in the IPCC, but which did not make it into the report at the end because the governments could not agree to put it. It's still in the report, it's not in the summary for policymakers. It shows you that, first of all, none of the regions is investing enough, but it shows also that investment needs to be increased massively, and lots of investments, for example, increases need to happen in Asia, and lots of the investment increases need actually to happen in the developing world. And this notion that we need to invest in the developing world has led to the perception that the scenarios don't depict a just transition. And this is I think, a big, deep misunderstanding that we had in the last IPCC report, because we know that the investments need to happen there, but the IPCC never said that the at Asia as actually to finance all of those investments. So in order to go to 1.5 degrees, lots of investments need to happen in the developing world, and we need to systematically think about ethical principles and fairness, given also the historical responsibilities of rich countries today, who actually needs to cover what fraction of the costs. And in a recent science paper, we looked into different equity considerations with a team of IPCC authors. And depending on how equity can be defined in different ways, yeah. So you can say, okay, equity means that everybody has the same per capita emissions rights from the past into the future. Then you will get to a certain fraction of investments that need to be made within the country compared to investment that need to be made outside the country. And what we try to show here is, given different ethical considerations, how much support or financial transfers need to happen, need to be actually provided from the rich OECD countries to the other countries in the world. And we were estimating this, so in the most favorable ethical or justice consideration, this is something around 200 billion US dollars per year, which is a relatively small number, $200 billion. It sounds like a big sum, but it's basically 50 coal power plants, if you wish. But up to sums which are almost $1 trillion, so $800 billion in terms of those transfers. These numbers are much higher than the transfers that are discussed at the moment in the international negotiations. So there is basically there is a fund that of about 100 billion that has been set aside, which has never been filled completely. But this is also illustrating why it's so difficult to get to agreement at the international negotiations, because we did not get to that point. And I have a few slides, but I stop here so that we have time for questions. Right, Sia? Do I understand your movement?
One or two sentences more.
Okay. No, thank you very much. I don't want to open. The other slides that I have was about decent living standards and how we can quantify minimum levels of energy. If you want to talk about this with me, we can talk about it afterwards. Thank you. Thank you.
Keiwan, thank you so much for your excellent presentation and providing us with ways of envisioning the rapid transformations while providing the co-benefits and also the multidimensional feasibility and also the decent living standards. I think you pointed us in the right direction. I would now like to open the floor for questions. Please, Professor Deutsch.
Looking from the side of energy system analysis, we have solutions, techno-economic solutions for a very fast transition. It's not an issue. The problem is on socio-political side, and I think you clearly said that. What I would like to have are good examples which are used to show how to do things. And we have willing governments which would like to have it implemented. I'm, for example, fascinated by Rio Grande do Norte, a state in Brazil, which is around 4 million people, that has 300% share of wind in its electricity consumption. And nobody knows about it, nobody talks about it. You know, they did it in 4 years, during one minister period. Mandate. You have Namibia, for example, that did go from 0 to 25% wind in 2 or 3 years. So why can't we have such examples, and then we can show this is the way to go?
Yeah, I think I cannot agree more. We need these best practice examples so that we can learn from them. Actually, I think they are quite some. I mean, there are many which show how to persistently stay on the ball in order to create an innovation environment that you can bring new technologies on board. Brazil is actually a good example. It's also you gave an example where you achieved this in 4 years, but Brazil has also shown that it can stay on the ball for 40 years. So the ethanol program, which was started under José Goldenberg in the late 1970s, José Goldenberg was the energy minister at that time, and we did together 15 years ago the global energy assessment. He basically introduced at that time a policy that made it possible for the farmer, for the sugar farmer in Brazil to sell the ethanol, if it produces from sugarcane ethanol, competitively at the gasoline station. And the difference was always paid by the state to the ethanol producer. That led to an unprecedented innovation. So ethanol became, but it took time. Yeah, so that's the lesson. Persistence is the lesson. This volatility in the policy process is poison. So if firms and farmers need to have a consistent signal that they can trust, then they are investing, and then the new technologies emerge. The same thing with the auctioning systems of the Germans in terms of PV. Germany thought, of course, that they would be the new PV industry in the future. Didn't realize that actually China will provide the PV cells cheaper. It's somehow a mixed story, but I think it's a good story at the end, because we want also that these technologies are produced not only in Europe, also elsewhere. Batteries, car batteries are the other example. So there are many examples. I think what they have all in common is that there is another co-benefit that the politicians have in mind as well. Yeah, so that's why this whole mobility transition needs to be seen also from the perspective of all the different benefits that I have been mentioning, because that's something that people can relate to. People, the public and the politicians cannot relate to only greenhouse gas emissions. I think that's something that I learned from my experience at the advisory board of Vienna, for example, or even the EU advisory board. When we presented our 90% reduction target to the EU Parliament, the Eastern European countries were not excited. I can tell you. But the reason for that is also that we did not have a discussion about so many other benefits that are there.
I see at least 2 more questions. One is from our colleague from Panama.
Thank you. My name is Rebecca Ramirez. I'm from Panama, but I'm working in Germany. And actually, my question is related with one of the graphics you were showing of this transportation sector, who can actually has a lot of emissions. And what are we going to do regarding all the shipping that we are producing, like international CO2 emissions? There is any strategy to avoid this? Because so far they are not counted for any country. So this is something that we will have to consider. Have you think about what are we going to do, or this amount of emissions are inside of this uncertainty quantification that you were showing in the beginning? Thank you. And thank you so much also for the presentation, which was very, very good. Thank you.
Thank you. Thank you. It's very kind. Yeah, so I think this is a very pertinent and important question. So it's not only shipping, it's actually also aviation. So both are international bunkers, which I would say there are very strange incentives there. I would actually say that shipping is moving quicker into the right direction than aviation. In aviation is still, I don't know whether you knew that, but kerosene is not taxed. Yeah, so basically because you don't burn the kerosene within the country, why should you pay within the country the kerosene? So everything that is burned in the very high up there is not taxed, because people cannot agree who should pay the tax, which is a weird, nowadays in the 21st century, a weird concept. So that needs to be tackled. I think that the difficulty with ships and perhaps aviation is also that so it will be very difficult to electrify. Not possible, I would say, to electrify. So we will need to switch there to, that's the sector where actually synthetic fuels make sense. In contrast to the recent European discussion to take e-fuels into our homes and into our cars, I think this would be the sector where they make a lot of sense. And it can only be solved at the international level, because one country alone cannot solve it, and that's why this sector is also falling behind. Yeah, so good. I cannot give you I cannot provide a political solution for it, but I think technologically what you need to do, and also what sort of policies would actually create also a more equitable solution is relatively clear. Yeah, thank you for the question.
One more here.
Hello. Hello. Hello, my name is Michael Gumhalter from AEE Intec in Austria. So you promoted basically the people should move towards energy services and services in general instead of goods, basically. On the other hand, you have rising trust issues of people with their politicians, with political systems, and with large tech companies, which would provide a lot of those systems also, of course. So how do you think does this conflict, and do you have ideas on how to get the urge of people to own their stuff and to be independent, how to get this out of people, which is of course also a rational fear and a rational idea?
Yeah, so I have to thank you for that question. I had actually a slide on this, but realized that I was hopelessly optimistic how many slides I can present. So I think the most important policies that we need is that we break up these monopolistic data providers. So that in order to increase trust within society, what you need is that you have a heterogeneous source of data providers. So we need public policies that incentivize exactly that, and also punish if data providers are abusing abusing the data power, yeah, because it's also a power play here. This is not really happening, so everybody is very afraid to touch it. I think the European Union has been going into the right direction. Perhaps the European Union is actually going too far, because if you make it very restrictive, then you lose the other aspect of it, that you want to share as much information as you can, so that you can enhance the efficiency of our system in a way. Yeah? But it's very clear that we need to have rules what data providers can do, and we need to, like Statoil. I think we are at this beginning of a new, not industrial, but a digital service society. And it's still the Wild West. Yeah? It's like Statoil, which was the only oil company at the beginning, which was then basically cut into pieces, and we need to, I think, do a little bit, don't quote me, but I think we need to do, we need to go into a similar direction also with the data providers.
We're having a very good discussion. Maybe I could add one more question from my side. We're on the critical decade for climate action. And especially the last 2 weeks has been very important. We heard emphasis on urgency, agency, and equity. We also had the launch of the YASA report on sustainable well-being for all, and how we can, also celebrating 50 years of YASA, but how we can also contribute to the post-2030 global agenda. Then this year we had the release of the synthesis report, where we also had the illustrative mitigation pathway on shifting pathways to sustainable development. K1, if I may, how do you see such themes going into the 7th assessment cycle? What can we expect in shifting these pathways for sustainable development?
So the question is, did you say the IPCC cycle? Right.
7th assessment cycle.
7th IPCC cycle. Yeah, I think at least this is what I observe in the scientific community, is that we need to make equity and just assumptions much more explicit in our analysis, and we need to design some of the scenarios that we do also together with those who at the moment have the perception that the scenarios do not cover their interests or their worldviews, right? So I think we need to have an even more inclusive scenario development process for the IPCC, and it has started. Basically, there is a process where everybody is invited to be part of that is deciding on scenarios for CMIP 7. I hope that those who are very vocal at the moment, those countries in international negotiations, will also be part of that process, yeah? Because that's the basis for the IPCC to pick up that knowledge. As you know, we don't do in the IPCC own research, so we need to make sure that the community is aware about those issues and that there are community processes that the IPCC can build upon. I hope this answers your question to some extent.
Are there any other questions? I would like to thank Keiwan very much for his presentation that enabled us to envision these pathways towards delivering sustainable well-being for all with co-benefits and system efficiency and also integration with renewable energy. I would like to once again thank our invited speaker. Thank you very much, Keiwan.
Thank you. Thank you. Thank you. Thank you.